Here's a question that sounds like it should have an easy answer. Is there a biggest prime number? Not the biggest one anyone has found, the actual biggest one that exists. You could imagine testing bigger and bigger numbers forever, hoping to find where primes finally run out. Over 2,000 years ago, someone proved you never will, and the proof doesn't require checking a single number. It just requires assuming primes run out and watching that assumption destroy itself. This is symmetry. Let's find the exact argument that proves primes never stop, no matter how far you count. Before the proof, the definition has to be exact. A prime number is a whole number greater than 1 that can't be split evenly into smaller equal groups. Nothing divides it except itself and 1. Take 7 dots and try to arrange them into a rectangle, rows and columns, with nothing left over. It's impossible, except for the trivial 1/7 arrangement. 7 simply refuses to split evenly into any smaller grid. Now take 12 dots. They arrange neatly into 2 rows of 6, 3 rows of 4, or several other rectangles. 12 is divisible by lots of smaller numbers. That difference is the entire definition. A prime number is a whole number bigger than 1 with exactly 2 divisors, 1 and itself. Every other number bigger than 1, called composite, has at least 1 more divisor hiding inside it. Lay out the whole numbers in order and mark every prime: 2, 3, 5, 7, 11, 13, 17, 19, 23. Notice there's no obvious rule to where they land. They're not every other number, not every third number, nothing so tidy. They thin out unevenly, sometimes clustering close together, sometimes leaving long gaps. This apparent randomness is part of why the question matters so much. With no visible pattern governing where primes appear, how could anyone possibly know for certain whether they eventually stop appearing altogether? Here's why primes matter beyond just being hard to divide. Take any composite number, say 60, and start breaking it into factors. 60 splits into 6 and 10, 6 splits into 2 and 3, 10 splits into 2 and 5. Keep going until every branch ends in a prime, and you're left with 2, 2, 3, 5, all primes multiplied together. Every whole number bigger than 1 is built this way, out of primes, and always the exact same primes, no matter which path you take breaking it down. Primes are the atoms. Every other number is a molecule made of them. One deliberate exception is worth pointing out. 1 itself is not considered prime, even though nothing divides it except itself. If 1 counted as prime, the atoms would stop being unique. You could always slip an extra factor of 1 into any factorization without changing the number at all. 60 would equal 2 times 2 times 3 times 5. Or just as validly, 1 times 2 times 2 times 3 times 5, forever. Excluding 1 isn't an arbitrary rule. It's what keeps every number's prime breakdown exactly one way and only one way. Here's the move that makes the whole proof work. Don't try to search for a biggest prime. Instead, assume someone already found the complete list of every prime that exists and see what that assumption forces to be true. Suppose, just for the sake of argument, that primes do run out, and here is the complete list of every single one. Call them P1, P2, P3, all the way up to some final prime, Pn. However many there are, however large the biggest one is, it doesn't matter. Just assume this list is total and complete. Nothing prime exists outside of it. That's the assumption. Everything that follows is going to test whether this assumption can actually survive. Now construct one specific new number. Multiply every single prime on the complete list together, all of them, into one giant product. Then add exactly 1, call the result n. This number isn't chosen randomly, and it isn't magic. It's built entirely out of the list itself, using nothing but multiplication and adding 1. Whatever n turns out to be, prime or not, it was constructed using only numbers already assumed to be the entire universe of primes. And that's exactly what makes it so revealing. Try to divide this new number n by any prime from the original list. Every single time, something identical happens. Pick any one prime from the list, say P1, and divide n by it. The big product part of n, everything before the +1, divides by P1 perfectly, with no remainder at all, since P1 was one of the numbers multiplied into it. But then there's that extra +1 sitting on top. Dividing that leftover 1 by p1 leaves, obviously, a remainder of exactly 1. So n divided by p1 doesn't come out even. It always leaves a remainder of 1 instead of 0. That wasn't special to p1. Run the same division using p2 instead, or p3, or any prime anywhere on the list. Every single time, the giant product part divides out perfectly because every prime on the list was multiplied into that product, and every single time, the leftover plus 1 produces a remainder of exactly 1. Not a single prime on the entire assumed complete list can divide n evenly. Every one of them leaves the same identical remainder. It doesn't matter whether the list has 3 primes or 3 billion. The argument never once looks at how many primes there are, only at how each one individually interacts with that leftover plus 1. The reason this holds for every prime at once, not just by coincidence, is structural. N was built as some multiple of p, whichever p you pick, plus exactly 1. Any multiple of p divided by p leaves remainder 0, always by definition of what a multiple is. Add 1 to a multiple of p, and the remainder becomes 1, always, no exceptions. This isn't a pattern that happens to hold for the primes we listed. It's forced by the exact way n was constructed. Here's where the assumed complete list runs into a wall it cannot get around. One more fact, already established back in part 1. Every whole number bigger than 1 breaks down into primes eventually, with no exceptions. Here's the short reason why. Take the smallest divisor of n that's bigger than 1. That smallest divisor has to be prime itself, because if it had a smaller divisor of its own, that smaller divisor would divide n too, contradicting the claim that we'd already found the smallest one. So n is bigger than 1, and n itself must have at least one prime factor, whether n happens to be prime itself or a composite number hiding primes inside it. There is no way for n to exist without some prime dividing it evenly. That much is guaranteed, no matter what n turns out to equal. So n has some prime factor, call it q, but every prime on the original list leaves a remainder of 1 when it divides n, which means none of them divide n evenly, which means q cannot be any of p1 through pn. Q is a prime, and it's not on the list. But the list was assumed to contain every prime that exists. A prime just showed up that isn't on it. The assumption has directly produced the one thing it said was impossible. This means the assumption itself was false. No matter which finite list of primes you start with, however long it is, this same construction always manufactures a new prime missing from it. There is no way to patch the list either, since adding that new prime and repeating the entire argument just manufactures another one beyond it, forever. A finite list of all primes is not just incomplete, it's logically impossible, which means the primes themselves never stop. There is no biggest one, and there never will be. This style of argument, assume the opposite of what you want to prove, then show it collapses, is called proof by contradiction, and it's one of the oldest, sharpest tools in all of mathematics. This isn't just an abstract argument, it works on real, calculable numbers every single time you try it. Try the smallest possible case. Suppose, absurdly, that 2, 3, and 5 were the only primes that existed. Multiply them together, 30. Add 1, 31. Is 31 divisible by 2? No, it's odd. By 3? No. By 5? No, it doesn't end in 0 or 5. 31 turns out to be prime all by itself, and it obviously isn't 2, 3, or 5. The tiny assumed complete list just failed, exactly as the general argument said it would. Push it further. Multiply 2, 3, 5, 7, 11, and 13 together, and add 1, 30,031. This time the result isn't prime, it splits into 59 times 509. Check the earlier remainder rule on this exact number if you want. 30,031 divided by 2, 3, 5, 7, 11, or 13, every single one leaves remainder 1, exactly as guaranteed, which is precisely why none of them could possibly be hiding inside its factorization. But look closely, neither 59 nor 509 was anywhere on the original list. n didn't need to be prime itself to make the point. Whether n comes out prime or breaks into pieces, every single piece it could possibly have is guaranteed to be a prime the original list forgot. Knowing primes never end is different from knowing how common they stay. Both turn out to be true at once. Infinitely many primes doesn't mean primes stay easy to find. Among the first 100 numbers, 25 are prime. Among the 100 numbers just below 10,000, roughly a dozen are. The gaps between consecutive primes grow, on average, wider and wider the further out you search. Primes really do get rarer, thinning out the way Euclid's proof never claimed they wouldn't. There's an entire theorem describing exactly how fast, called the prime number theorem, and it took mathematicians over 2,000 years after Euclid to pin that rate down precisely. But rarer is not the same promise Euclid made. His proof only claimed the supply never actually runs out completely, no matter how thin it gets, which is a much narrower and much stronger promise than primes are common. Not every question about primes is settled this cleanly, though. Look closely at the list, and you'll spot pairs sitting just 2 apart. 3 and 5, 11 and 13. 17 and 19, 29 and 31. These are called twin primes, and mathematicians have found staggeringly large examples of them. Whether infinitely many such pairs exist is called the twin prime conjecture, and unlike the question this entire video just answered, nobody has ever proven it, one way or the other. Euclid's argument closed one ancient question completely. This one, just as old in spirit, is still wide open. That guarantee is why people still hunt for record-breaking primes today, using volunteer networks of thousands of ordinary computers, donating spare processing time to a decades-old project, running for months at a stretch on a single candidate number. Nearly every record in recent memory has been a specific shape, called a Mersenne prime, one less than a power of 2, because that particular shape happens to make testing enormous candidates for primality dramatically faster than checking an arbitrary number of the same size. The largest ones found so far have tens of millions of digits, far too long to ever write out by hand. None of them are anywhere close to the largest prime that exists, because Euclid's proof already guarantees there isn't one. Every record is temporary by mathematical necessity, not by lack of trying. There will always be a bigger one waiting. So there is no biggest prime, and the proof never had to search a single number to know it. Assume the primes run out, build one specific number from that assumed complete list, and the construction itself manufactures a prime the list forgot every single time, without exception. That contradiction is the whole argument. 2,000 years old, and it still hasn't needed a single update. If you want more ideas like this explained from first principles, subscribe Symmetry. See you in the next one.